Okay, I'm doing the YouTube live. I'm starting it.
Yeah.
Okay, I started all the recording and video.
So we can go.
Yeah, I think we can start.
Okay, just a few words for this morning. First, hello everyone, and welcome for this for the last day of our joint meeting for the Lava and Eve programs. Yesterday we saw some very interesting case of volcanic crises and how the civil security authorities deal with them, with example from Hawaii, Congo, Comoro Island, and the Galapagos Island. We saw situations that were sometimes very different, and social conditions that were also very different. And I think that this diversity shows a great value that a meeting such the one we have now can bring. Today, the program is also very rich. This morning, we will hear our Italian colleague, Sonia Calvari and Alessandro Bonacorso, who will present the flank major eruption at Mount Etna. Then Domenico Mangione, Stefano Cioli, and Luigi Coppola will present the civil protection aspects in Italy. We will then go to Iceland with Thor Thordarson, Arman Holskulsson, Olaf Kjartansson, and Palle Bortordóttir. I'm sorry for the pronunciation, it's not very easy with the Icelandic name. They will talk about the management of volcanic crisis in Iceland, and we hopefully will have some news about the eruption in the Reykjavik Peninsula. And this afternoon, we will have the conclusion of our expert elicitation exercise by Alessandro, Alessandro, Julie, Andy, and Andrea Bevilacqua. And then we will have a short reminder on the AF project by Joan Marti before starting a session of discussion and conclusion of this workshop. Okay, now I propose to start, and I give the floor to Sonia Calvari. Sonia, you can go.
Good morning to everybody. Can you hear me?
Yeah,
perfect.
It's okay.
And can you see the video properly? Because I cannot see anything else than my screen. So
yeah,
everything works.
Yes, we have your first slide online.
Thank you very much. Good morning to everybody. I'm going to show you a few examples of effusive eruptions that we have been dealing with on Mount Etna. And first of all, I will show you something about the typical activity of Mount Etna and what we have discovered during the last few decades of the behavior of this volcano. First of all, the main way Mount Etna releases its inner energy is through flank eruptions. In this map, you can see Mount Etna in gray and the most recent flank eruptions in red. You can see that we had 55 major flank eruptions occurred in the last 3 centuries, starting from 1669 to 2008. You can see that they were very widespread, especially along a north-south direction, but also east-west. Most of the lava flows went inside the Valle del Bove, which is this big depression that cuts the east flank of the volcano. And the most destructive eruption that we had was the 1669 eruption that was opening from a fracture that opened at 700 meters elevation on the south flank of the volcano, just in the middle of the town of Nicolosi, and spread south towards the town of Catania, so destroyed Nicolosi, several other towns, and also the western part of Catania. But we had also other important eruptions that were threatening villages, like the 1981 Randazzo eruption on the north flank, and the 1928 eruption towards Mascali. And of course, the 91 to 93 eruption that was going close to the town of Zafferana Etnea, and was the most impressive eruption that we had during the last 3 centuries. Here is a picture showing a painting, an old painting that is shown in the Catania Cathedral, showing the destruction caused by the 1669 eruption. You can see here the Monti Rossi cinder cones that were growing thanks to the lava fountainings occurring during the first stage of the eruption, and the lava flows spreading south towards Catania and reaching also the harbor of Catania. The 1669 eruption had a maximum lava flow length of 15 kilometers and an erupted volume of 600 millions of cubic meters. 6 villages were destroyed by the lava and also part of the town of Catania. And here is the situation of Sicily, of Catania now. You can see that if an eruptive fissure like the 1669 should open now in the same place with the eruptive cones of Monte Rossi shown by the ellipse, the red ellipse, you can see that the damage is will be estimated in 7 billion euros by a work done by Del Negro et al. In 2016. Another example of a major effusive eruption that destroyed the town occurred in 1928. The town of Mascali was covered by lava. The town of Mascali was destroyed and completely rebuilt. And at that time, a few years later, in 1933, there was an important law that decided to store official funds for the building up of the Osservatorio Etneo at the University of Catania. And this is the second European volcano observatory, because the first one was the Osservatorio Vesuviano that was instituted in 1841. We had other important effusive eruptions that were approaching villages, like the 1981 Randazzo, the 1983 again in Nicolosi, the south flank, and the 1991 to 1993 eruption that went toward Zafferana Etnea, where eventually the second successful attempt to divert the lava flow was realized. Here is a map showing the 91 to 93 effusive eruption. This was very important because of the duration of the eruption was 1.5 years, because of the volume of lava erupted. The 240 millions of cubic meters was the largest and longest eruptions occurred during the last 3 centuries. And also because of the successful lava flow diversion that was realized at that time. But especially the huge amount of data that we collected during the eruption allowed us, and especially the analysis carried out after the end of the eruption, allowed us to recognize that at that time it was extremely important, the development of lava tubes, here displayed in red, during the first phase of the eruption from December 91 to May 92, and also during the second phase of the eruption from the 27th of May, when the diversion was realized, up to the end of the eruption. Why it was so important to the development of these lava tubes? because at that time in 1993, everybody was convinced that lava tubes form just within Pahoehoe lava flows and not within flows. And instead, this very long, something like 8.5 kilometers long lava tube network developed during the eruption, but especially within lava flows. The main difference between flows and Pahoehoe is that flows are normally connected to high effusion rate eruptions. So the possibility of having lava tubes developing within flows meant that we had the formation of this very long network of lava tube feeding lava without heat loss or virtually without heat loss for 8 kilometers up to the outskirts of Zafferana Etnea that is located here. As you can see, only less than 2 kilometers from the most advanced lava flow front. When eventually the lava flow diversion succeeded, the lava tube network was deactivated. There were no lava crossing the lava tube, and the new lava flow field that developed also thanks to a significant decrease in the effusion rate was much smaller. The second phase of the eruption, also if lava tubes formed also during this second stage, did not allow the lava flows to progress for more than 4 or 5 kilometers from the vent, from the main vent. And here is a few sketches showing the importance of lava tube and how they managed to increase enormously the maximum length of the lava flow field. Here is a view of a few sketches showing how lava tubes develop within flows, essentially for joining of the two levels where there are narrow channels, or by the sealing of the outer crust in a wide channel or on the flow front. And as soon as the lava crust cools around the main flow, we can have the inflation of the flow and then the budding, the start of a new breakout from the flow margins. And if you can see this graph on the right-hand side, you can see the maximum length reached by the initial flow with the black circles, followed by a new breakout, the open circles, increasing the length of the flow because the lava was traveling within the first flow, within tubes. And then the final length of the total lava flow field was 8.5 kilometers, then much greater than the initial flow that formed during the eruption. And in this photo on the left-hand side, you can see in black the lava flow field and the eruptive fissure, and you can see a number of white holes revealing the path of the lava tube because these were skylights with carbonate precipitate forming around it and then revealing the position and the distribution of lava tubes. But also studying the lava tubes, the old lava tubes in this case, this is from the 1792-1793 eruption on Etna, we could relate a number of inner features of the lava tube to what happened within the tube while the tube was still active. And these are two examples. The left-hand side is from a tube close to the eruptive fissure, something like 2-3 kilometers. And you can see that the inner coating is made of a high number of very thin coatings, something like a few millimeters, and several inner coatings, like 10, 15, or even more. Whereas at the end of the lava flow field, the right-hand side is showing this situation. We have just 3, maybe 4 inner coating, very thick, something like 8, 10 centimeter thick, related to a different stage of the lava flowing within the final part of the lava flow field. It was more viscous, more crystallized, and the number of inner coating revealed the number of pahoehoe lobes being fed by this tube. From the end of this lava tube, in fact, we could see 3 lobes, 3 pahoehoe lobes being fed by this tube, whereas in the other example, we could find a very big pahoehoe flow field being fed by this tube. So the number of coatings is revealing how long the lava tube itself was active, and because in order to have one coating, we need that the tube is completely filled with lava and then drains because of the breakout opening up the flow margins. By especially analyzing past sections of lava tubes, we could see that we have a triangular section when normally the lava tube develops within an eruptive fissure, or a rounded section where it's developing within a lava channel, or we have an asymmetrical section when the tube is bending on one side or another. But the most important surprise was how common is this keyhole section that is revealing an important process occurring while the lava tube is still active and is sort of sealing. This keyhole section develops when we have the vertical merging of 2 overlapped flows or 2 overlapped tubes. When the upper tube collapses with the flowing lava within it, collapses within the lower tube, which has the roof not yet completely sealed. And this is a process that is very important and is very common on Etna, because it allows the upper lava to feed again the deeper tube that is normally much bigger than the uppermost one. And during the 91 to 93 eruption, there was an important attempt, well described by the papers from Franco Barberi and Marcella Carapezza back in 2004 and also in 1993. As I said before, the lava flow field was approaching the town of Zafferana, and because of the possibility of confine the lava flow field within the Valle del Bove, within this deep valley, eventually in January 1992, the civil protection decided to build up this earth dam that is shown here on the left-hand side, on the left image, that was 200 meters long and something like 20 meters high. And this simple earth dam managed to confine the lava flow field within the Valle del Bove for several months. Eventually, on the 7th of April, there was the first flow covering the earth dam and passing on top of it, and then threatening the town of Zafferana Etnea. And this is when the first attempt to divert the lava flow was tried here, but it was extremely dangerous, extremely difficult, and did not manage to succeed, because in this position, the network of lava tubes was very braided. So there were a number of lava tubes active. And this is why eventually the civil protection decided to operate an artificial diversion at very close to the eruptive fissure. It was excavated an artificial channel on the flank of the master tube, and then eventually throwing big concrete blocks jammed together with metal chains within the lava tube. It was obtained that the lava tube was completely obstructed with the lava flow coming out, and then they blew out this thin wall separating the master tube from the artificial channel in a way to make the lava flow being diverted inside this artificial channel. And as I showed you before, eventually also the effusion rate decreased, and then the new lava flow field did not manage to destroy the town of Zafferana. So dealing with effusive eruption, the most important parameter to keep under control is the effusion rate. And together with Andy Harris, we have been collaborating for several years now, back when he was in Hawaii, and also now that he's at the University of Clermont-Ferrand, trying to measure this parameter, the effusion rate from the ground, from satellite, and also from helicopter using a thermal camera. But why it is so important to measure the effusion rate? Because back in 1971, George Walker discovered that the effusion rate is directly related to the maximum length of a lava flow. And in 1998, together with Harry Pinkerton, we analyzed a number of lava flows from Mount Etna to calibrate the previous formula from George Walker just for Etna. And we came out with this simple formula that allows us, as soon as we have the peak effusion rate that is normally measured during the first few days or few hours of an eruption, to estimate the maximum length of a single lava flow, so without lava tubes, just a single lava flow. And applying this formula in the 2001 eruption of Etna, where we measured a peak effusion rate of 30 cubic meters per second, we could calculate that the maximum distance that the flow would have traveled was 6.4 kilometers, and the real distance was just 100 meters more. But again, and this is a paper published with Andy Harris in 2011, analyzing the effusion rate and obtaining the cumulative volume erupted by Mount Etna during the last few decades, we could recognize that Mount Etna on a long time keeps a very steady behavior, which is characterized by the intrusion within the supply system of a volume of 25 millions of cubic meters per year that can be released in different ways. And this is a result that we obtained together with Alessandro Bonacorso and was published in 2013. In fact, analyzing the eruptive behavior of Mount Etna between 2011 and 2015, we could recognize that the volcano can release the volume of magma accumulating within the supply system in two different ways, or producing a high number of explosive eruptions like the Farfantonings that normally release something like 2.53 millions of cubic meters per each event, or with a smaller number of effusive eruptions that normally release 30 to 60 millions of cubic meters. So back in 2002, when Mount Etna was producing a new flank eruption, we had the southeast crater active, and we measured at the base of the lava channel spreading from the south flank of the southeast crater an effusion rate of 15 cubic meters per second. And using this simple formula, we could recognize that the maximum extension that the lava flow could reach was 4 kilometers. Unfortunately, this is the distance between the southeast crater and the Rifugio Sapienza area. So we recognized well on time and we advised the civil protection of this possibility. And this is why the civil protection decided to build up a small earth dam that was not confining but slightly deviating the lava flow, the 2002 lava flow, making it overlap the 2001 flow. And here is a view of what happened. There was also a lava flow simulation carried out by Gianni Macedonio, which confirmed the path followed by the natural lava flow, and then the artificial barrier displayed here in yellow that was built up by the Civil Protection Department on the 23rd of November. And although if this earth dam was slightly overflowed by the flow, it managed to divert the lava to protect the Rifugio Sapienza area, and the lava flow was stopping just as soon as it reached the road, so as soon as it reached the 4 kilometers distance. So since then, we started in carrying on some monitoring of the active lava flows using helicopter and mapping the active lava flows using thermal cameras, and also estimating the effusion rate from satellite. And we came out with this HotSat satellite thermal monitoring system that uses different kind of thermal images from satellite to detect the hotspot and obtain from it the time average effusion rate. And these values is eventually used to simulate a lava flow. Here you can see a simulation of the lava flow carried out during the 2006 July Etna eruption using the effusion rate estimated on the basis of the MODIS data. And you can see in red the simulated lava flow, and with the blue outline the real lava flow. And the slight difference between the two close to the eruptive vent is because of the DEM not being very well updated. And again, with the lava flow simulation, we can also estimate the lava thickness, and we can also realize lava flow hazard maps that give us the invasion probability once we know the effusive vent established. And eventually we came out also with this Lava Tazza platform that uses 4 different modules: satellite application, hazard map visualization. It uses also a database of 30,000 simulated lava flows, and the real-time scenario forecasting that is updated in real time using the MagFlow software on a CUDA architecture. And this is a view of how the system works, and an application during the 2011 eruption. And we use also a vent opening probability that is continuously updated using the monitoring data that arrived to the control room at INGV in Catania. And here is another application obtained for the 2002 eruption, where as soon as we know the position of the eruptive vent, we can immediately provide a short-term hazard map that was immediately updated as soon as we knew the real position of the effusive vent. You can see here going up and down how the active flows change their distribution on the basis of the active vent. Thanks for your attention.
Thank you, Sonia. Now I propose to have Domenico Magnon, and we will have the question after the 2 presentations in a group for Etna Volcano. Domenico, can you share your screen, please?
Yes. Okay.
Perfect.
Can you see it Full screen now.
Yeah, we have it in the full screen. You can go.
Thank you so much. Okay, so this presentation has been set up with the contribution of Stefano Ciolli and Luigi Coppola. We all three work in the Italian Civil Protection Department, the national level in Volcanic Risk Unit. And this presentation will deal with a broader theme in respect of what Sonia just presented, meaning that we're going to talk about how we manage volcanic crisis in open systems in Italy. This is the roadmap. Let's see the 5 targets of the presentation. We will start with a very short introduction about the National Civil Protection Framework. We're going to talk about the National Volcanic Warning System, how is it composed, and then we're going to go through the long-term volcanic risk management, the short-term volcanic risk management, dealing with open systems. And then we will conclude with the early warning systems that we have online now at both our volcanoes that we're going to talk. National Civil Protection Framework, to say that volcanic events, we have 3 types of events in our National Civil Protection Law. We have A-type events, B-type events, and C-type events. The main difference between these 3 is the extent and the impact. So based on this extent on the impact, this could be faced by local level, means municipality. These are the A-type events. If the extent and the impact is larger, then you will have a contribution of more municipalities or the coordination from the regions. And if the extent is really big, then there is the government providing support in emergency management. Where are volcanoes? Well, volcanoes are borderline. We have volcanoes that with its activity may be categorized in the B-type events, but sometimes volcanoes make large eruptions with a large impact that needs to be faced with extraordinary efforts by the government, so from the National Civil Protection Department coordinating a large number of bodies. This slide demonstrates the coordination system of the Italian Civil Protection Department once a national emergency is declared. As you can see here, I'm sorry, but the writings are in Italian, but just to show you how many subjects we have sitting around the table. And this table is an operational table, a decision-making table. So it is a system. This is what we call the National Civil Protection System. And what's missing here, but it's sitting at the same table, is science. Scientists are embedded inside the civil protection system and take place in a decision-making table. Okay, so we work very, very connected with science, and they sit at the decision table. This is just to show our organization of the Civil Protection Department, why I put this slide on. Because we have a volcanic risk unit inside the structure of the Civil Protection Department. So we have a semi-scientific unit that talks with emergency management. We have an office for the emergency management. But still, we talk directly with volcanic observatories, so mainly INGV with its different sections, and the other research institutes that are part of the system. These are the actors, scientific actors. So you can see we have actors dealing with hazard, actors dealing with vulnerability. So mainly we have the most important one, which is INGV, which is appointed by a law as the institute providing monitoring and surveillance. And then we have other research institutes like University of Firenze, like the National Council for Research, which deal also with monitoring, give us a different type of monitoring, or sometimes it is complementary. This is another strength that we have in our system, because most of the time these systems are quite complementary. So we have a unique view of what's happening coming from 2 different parts. And which is the main, let's say, box in which this is regulated? It's agreements. We have specific agreements with these research institutes, other than obviously the law that I said before that regulates the INGV activity. So we have specific agreements, and we also try to set up applied research project. We fund applied research projects in which we express our needs, our requirements in terms of, for example, early warning tools, or for example, long-term hazard maps. And INGV usually coordinates this table and calls together also other partners like universities to put together the know-how and reach the target that we asked. So in the right part of the slide, as you can see, these three, the three main actors talk together. So it means scientific community, we talk with them, but we also talk with other stakeholders that may be, for example, the other components of the national civil protection system that might benefit from scientific information. And then in the bottom, you see the CGR, means Commissione Grandi Rischi. I hate translating this because it is awful, so I just left it in Italian, Commissione Grandi Rischi, which is the most important in the scientific advisory group, let's call it like this, appointed by the Prime Minister, and is made of experts dealing with lots of disciplines, and also for volcanic risk. The National Volcanic Warning System is based on alert levels. We just revised alert levels in 2015. Now we are going through another update we started in 2019 and it's still ongoing. We are revising, for example, the alert level system for Stromboli, the alert level system for Etna, but the main structure is the same. So it's based on 4 colors from green to red. The colors just tell us which is the eruptive activity. It's low, medium, high, very high. And the alert level table contains the expected phenomena. So it's based on what we see, what we might expect based on the historical, on the past eruptions. So based on experience. And also which are the possible impacts on the territory. Then when we assess the alert level, the operational part assesses the operational level. As you can see here, we have 4 operational levels or phases. It's the same. They go through base, warning, base, warning, pre-alarm, alarm, and these ones just contain the actions, the emergency management actions. I want to stress that there is not a correspondence one-to-one with this, which means that if we're green, it doesn't mean now we are in base, or if we are yellow, we could be in pre-alarm, depending on, for example, exposure, depending on vulnerability of the moment. So it's not related one-to-one with the alert level. And the same operational level, but maybe different for choice, is also at the local level, the regional level, for example. Here is for example, the regional operational phases, where you can see base is missing, because obviously in open systems like could be Stromboli or Etna, the risk is not always 0. So you will never have a base level, because if you go on the top and touristic activities go on the top, you are always exposed to volcanic hazards. The volcanic protocols are very strict, and these are also included in those agreements I said before. Depending on the situation, we receive 4 types of products. So in case of a sudden event, we will receive a volcanic advice. And these things come from mainly INGV, which I want to stress has the surveillance task. So advices, it comes within 5 minutes from a sudden event. Then we have multidisciplinary bulletins that are issued weekly or daily, depending on the alert level. So for example, in alert level yellow, it would be weekly. If we go to orange alert level, then it could be also daily. Then we have special advices, and these come within 12 hours in yellow or green alert level, or in 6 hours from the first advice in orange and red. And these special advices are rich of information. It's just not the information given in the advice. Something happened, but it's more information collected from the field survey, more information collected from monitoring network. And sometimes also scenarios are included in this type of documents. Then we have the reports. Reports are issued every 6 months for all the volcanoes, or on specific decision of the INGV, or on request of the National Severe Protection Department. As I said before, all of this is coded inside the agreement and is coded inside a document called Procedures for the Exchange of Scientific Information that has been delivered to all the scientific partners dealing with us and working with us, and so they stick to it. So if INGV issues a bulletin weekly or daily, same does University of Firenze, same does, for example, also CNR IREA, depending on the alert level, obviously. But all of them stick to these procedures. So this is the distribution of the Italian volcanoes. As you can see, there are almost everything in the southern part of Italy. In bold, in the blue box, you see the volcanoes on which we are working on the alert levels, and on which we are actually working also on the emergency civil protection planning. On the right table, you see our open systems that are Etna and Stromboli. Etna is ongoing. The eruption is ongoing. Stromboli last erupted, if we can say this. I know many volcanologists would say, hey, Stromboli is always erupting, but I intend a major eruption. He erupted in 2019, and it was an explosive eruption followed by an effusive phase. Then we have Vulcano, Vesuvio, Campi Flegrei, and Ischia, which are closed systems, and we are not going to talk of them today. Why it's not going anymore? Yeah, okay. So sorry, the red box. So this is our 2 target volcanoes of which we are gonna discuss today. Stromboli, many of you know it. For those who don't know it, it is a volcanic island in the southern Tyrrhenian Sea. This height is 1924 meters above sea level, but extends underwater for another 2,000 meters. Last eruption, as I said, 2019, always active. Could be very easygoing situation, only 2 villages in terms of exposure, but there's a but. 400 people live there, but in the summer period, obviously it's a beautiful place, it's a real attraction for tourists. Then you can have daily numbers of tourists reaching several thousands. And these tourists, they don't know where they are, really. They go to Stromboli, they look like a mountain. They don't know this is a volcano, and they don't know the hazard, they don't know what to do. So this is a major issue during the summer period in terms of civil protection, volcanic risk management. These are the main hazards coming from Stromboli, very few. As you can see, little island, many hazards, mild to violent Strombolian activities, lava flows, landslides, pyroclastic flows, wildfires, tsunami. Lahars is missing. Let's see what we can do with them. But I mean, there's a lot of hazards coming from this island, so you can understand the issue during the summer period for this volcano. What is in the red box are the phenomena that are targeted in our national emergency plan, so the national level impact scenarios. Okay, and why I said also landslides, for example, or pyroclastic flows, because they both are triggering tsunamis. So lava flows, landslides, pyroclastic flow, once they enter into the water, they might trigger tsunamis. that for its impact and extent it needs to be faced by national government means. Mount Etna is the second target. The last eruption is 2021 is still ongoing with a question mark because hope it finishes soon. I mean, it's been a lot of eruption and a lot of stress on the territory due to the ash fall. The population involved is about 900,000 people living surrounding Mount Etna, exposed to several hazards, which are, again, violent strombolian explosions, again, lava flows, and this time we have ash. Ash is a really big problem for the downwind inhabited populated areas of the volcanic area. But we have also some other cascading hazards, which are pyroclastic flows due to collapses of sectors, for example, of the cones, like happened recently in some of the lava fountains, strombolian eruptions from February to March. Or you would have wildfires, of course, in case some fragments fall into the vegetation or the lava flow enters a forest. In terms of long-term volcanic risk management, we had to choose which national impact scenarios to plan on. So we chose that local impact scenarios would be the strombolian activity. So this type of activity, this type of hazard is dealt inside the local civil protection plan, while the national impact scenarios, as I said before, are collapses of the Sciara del Fuoco, which is the main structural feature that could collapse in case of magmatic intrusion and generate tsunamis. Effusive activity outside the Sciara del Fuoco, but is very, very rare. Or sector collapses, means huge collapses of the Sciara del Fuoco, and this type of event is still rare. And this is because we only chose the collapses and tsunamis generated by magma intrusion, like the one that occurred in 2002. So together with INGV, as I said before, we funded several applied research projects, civil protection oriented projects, to match and to simulate what would be the tsunami arrival times rather than the tsunami inundation modeled by inside this project, in order to fit what was the observed area of the tsunami of 2002. And based on this, we chose the inundation area of the National Emergency Plan. Okay, so based on this, then we do the actions. What we do in case of an impending tsunami. For Mount Etna, we made the same strategy. So we first identified the local impact scenarios, which are summit explosions, summit lava flows, or lava flows that go into Valle del Bove and do not threaten populated areas. While for national impact scenarios, we just highlighted two of them, which could be Plinian eruption of Mount Etna, or lava flows threatening or going into populated areas. Again, the first one, Plinian eruptions of Mount Etna, is very rare. So we concentrated on planning on lava flows threatening villages from lateral eruptions rather than from well-fed summit eruptions. So what we've done is basically, again, this is a product. The map on the left is a long-term hazard map, inundation map coming from a work of Del Negro et al. 2013. This is being funded by a civil protection project from 2007-2009, and this is what has come out. Based on this hazard map, we issued, but it's still in draft, the reference scenario that we give to the municipalities. On the right, they issue their local emergency plan to face eventually a lava flow, an effusive eruption emergency. Well, the situation is very simple, as you can see. We have 20 municipalities that are just around Mount Etna, and almost each of them reaches the top. So what I like to highlight is to our colleagues of the regional civil protection, keep calm, because there are only 20. So it's really hard to coordinate all these municipalities during every eruption, because each one has its own operational guidelines. And for example, if there is a regulation made by one municipality, it doesn't mean that also the neighboring municipality would do the same regulation. So it's really tricky, and it's really a hard work for our colleagues of the Regional Civil Protection Department. In the short term, things change a bit. We don't have two separate scenarios. It's just the same flow. For example, we have information coming from monitoring network, volcanic observatories, and research institutes. We have regular conference calls with them, means every month. We could ask Commissione Grandi Rischi for an advice if this is needed. After the conference call, we assess the alert level, and we transfer this information to the stakeholders that are sitting at the conference call, which are the regents and the other and the scientific community, obviously. And what happens? So this is an explosion of the diagram of the diagram I showed you before. So, for example, we receive the information. This information is evaluated at national level. If necessary, we do the conference call, but at the same time, the region could issue its own regional advice indicating civil protection actions to the municipalities, enabling then the local response. What the municipalities do is to take mitigation actions, like, for example, applying what's on the local civil protection plan, or issuing specific regulations. And these apply to excursionists that are on the volcano, or directly to the population. The last but not the least is the early warning systems. Why early warning system? Because on in open system, phenomena are very, very rapid. Sometimes are extremely rapid. So we need to shorten the time. We need to shorten this flow, and this is possible only with early warning system. The first one I would like to mention is the one that is on Stromboli, dealing with tsunamis. So it's managed by Università di Firenze. It is completely automated. So basically, when the two gauges that are on front of the Sciara del Fuoco record a tsunami, they automatically trigger the alarm system that is installed on the island and on other several islands. The second early warning system is again on Stromboli, but this time is dealing with violent explosive activity like the ones we recorded in 2019, paroxysmal explosions. This time, this system is able to recognize several minutes, we're talking about minutes, before a paroxysmal explosion occurs. And again, this type of system enables the local alarm system, the sirens that are on the island. There is another system that it's more like, it's not really an early warning, but it's more a decision support system, which is combined by INGV and by University of Firenze, which gives us information about a possible evolution of the activity from explosive to effusive. And this is very important because in that boundary from explosive to effusive is where the dikes really intrude inside the Sciara, and is the moment in which you would have the highest probability of collapses on the Sciara del Fuoco and eventually a tsunami generation. Finally, on Mount Etna, we have an automated lava fountain detection and intrusive warning. This is ran by both INGV and Università of Firenze. We go in detail just in a moment. what I like to say is that all of this is not really, I mean, it's working, but it's still in experimental. So it's been set up since very short time. So we need to test its efficiency, and we're still working on improving the system. This is a screenshot of the last, the one that I mentioned. So the first box, Etna Summit Activity Warning, is the one, is the early warning for the lava fountains, let's say. And the second box is the Stromboli eruption warning, is the decision support system I was telling you before for the transition between explosive and effusive regime. If we explode the Etna activity warning, you would see it's very complex. I mean, it's made of a lot of subsystems, and each subsystem is an alert system. So for example, you would have the thermal alert system, the tremor alert system, the EW means early warning based on infrasonic parameters of Università di Firenze, and these things all are combined inside a unique system that makes an ensemble in the box, in the white box in here. And depending on the parameters recorded and depending on the status of each subsystem, you would have an A0, A1, A2 message that describes what's occurring. And this enables several hours before, hours for 2/10 of minutes at least, to the local authorities to take mitigation action for those who are exposed to summit explosive activity. Finally, we have another tool inside this box that is the intrusive warning, which is very useful for us at national level because we could really know if there is an intrusion going on the flank of the volcano and where it is. Because together with this, you would also see on the right, the first box with this red cloud is where the most probable lateral vent could open based on what's recorded by the GPS or the tilt meters. And again, here you would have modeled the source. So basically, if there is a dike, you would see here a red dash, which means that the dike is here, and you would probably have an erupted fissure here. This worked pretty well in 2018, doing a back analysis. So based on this, in the intrusion that we had in 28 December 2018, don't tell me why these volcanoes erupt always in December and near the Christmas period, don't tell me. But the INGB saw the intrusion at least 1 hour before it occurred. So this is it. Thank you very much, and we are here for your question if you have it.
Thank you, Domenico, for this very, very clear presentation. So we have maybe about 20 to 30 minutes for question now. We can delay a little bit the presentation on Iceland crisis management because we will have time in the open discussion. Arman, I see you are online. I don't know if it's you are doing the presentation about Iceland volcanism. So
I'm ready with everything, of course.
Okay. Okay, we can start with it's good to see you, Arman.
Hi.
We can start after the question about the Italian volcano. So I see that Stefano and Lucia still have their hand up. Woman first. Lucia, if you want to ask your question.
Yeah, first of all, hello, Sonia and Domenico. It was great to see Italy for me. And also, Sonia, you remind me the time during which I was students in 1993, the other century in the other millennium. And so I have a question for you, speaking about this incredible mission of Franco Barberi, that at the time was my professor, and we were so proud of him. Now, in 2021, how do you vision what he did, this kind of is this kind of thing that try to deviate the lava. Was a good essay, was a lot of money, would be able now, so it's a little bit for Dominique as well, the civil protection will be able now to do it again, or after 20 years now, more than 20 years, you will come up with something different. I'm a little bit curious to see, sometimes things that have been done in the past are difficult to be reproposed now, like to go to the moon again. So I wanted to know your vision about that. I was impressed at that time. I was so impressed. So I'm curious now.
I'm old enough to have participated in the monitoring of the 91 to 93 eruption. And I did my PhD with Harry Pinkerton after analyzing the data and analyzing the distribution and the formation of lava tubes. So I remember very well. And Domenico will explain better probably the position of the civil protection, but from a scientific perspective, I think that the 91 to 93 eruption was unique. It was unique because we had a very long-lasting lava flow. The eruption lasted 1.5 years, threatening the town of Zafferana, but spreading mainly within the Valle del Bove. So first of all, it was possible to build an earth dam without causing major diversion towards other villages, because the earth dam was just confining within the desert Valle del Bove, the main active lava flows. So that was possible because of this reason. In 1983, it was the first time a diversion was attempted, but the situation was very different because the lava flow was outside the Valle del Bove, towards south and towards the village of Nicolosi. In addition, also the second diversion, the one that was eventually successful, was carried out again within the Valle del Bove, along the eruptive fissure. I think, to be honest, that the amount of money spent was really too much. This is my vision, but it's obvious that it was a great example, and I think that it's very difficult to happen again, also because the laws have been changing. Now the Italian government is very careful with lava flow diversion. For example, the example that I showed about the 2002 flow, it was possible to slightly divert the flow because it was just covering a previous flow, not just going on new land, because in this case, obviously, it's a big problem, it's a big issue. So going back to the 91 to 93 eruption, the lava flow diversion was successful, especially because of natural reason. The effusion rate decreased dramatically, and the new flow field that formed didn't have enough strength, enough power, enough effusion rate, I would say, to build up a new extensive lava flow field with extensive lava tubes like it happened during the first phase of the eruption. So it's hard to say, to be honest, but perhaps if the lava tube was left active for longer without any diversion, for sure it will have reached the town of Zafferana, because it was very close by. I don't know if I managed to show well, but
yeah,
the most advanced flow was just less than 2 kilometers from the main houses of Zafferana. So, but it was unique, I think, and the situation is difficult that we can have a similar eruption, and it's difficult that we can have a similar situation where it's really safe, let's say, to try a diversion.
Okay, thanks a lot.
Who wants to add something?
Wait, Domenico.
Well, what Sonia said is really correct. I mean, I wasn't there in 1991, but I think that nowadays in 2021, if something occurs like this, we are talking about vents opening in the summit areas, obviously. So you have time to think on what to do. Then I probably think that there will be a cost-benefit analysis based on how much is the cost for the barriers, rather than what could be the cost of the impact of the lava flow, and if this really threatens populated areas. I don't know other techniques really to divert lavas. I mean, lavas are like bobcats that just destroy everything. So it's really difficult to think about something different. If something happened, if an effusive vent opens at the lower heights of the volcano, that could be a problem, because probably you wouldn't have the time to organize anything, and the most important mitigation action could be evacuation simply, and accept that the lava flow could destroy houses. I don't know if Stefano wants to add something to this.
Yeah. Okay,
Yeah.
thank you. Yeah, Stefano, you want to say something?
No, can I add something?
Oh, Gianni.
Because during that eruption, we have learned a lot about the diversion of lava flows. For example, we have learned that a barrier that is built on the front is less effective than a diversion made near the vent. And the diversion must be projected in a way that even a small barrier should be able to divert the lava in a path that is able to receive the lava flow. So, in principle, the project of the diversion should be done selecting a point near the vent and allowing the lava to choose another path that is possible. So you cannot do a diversion randomly by putting a barrier somewhere, but they should put the barrier in a given point, and there should be the condition for the new lava path to follow the other direction, the other path. Otherwise, this diversion is not effective. And also in that let's say experiment, there were been many techniques that were experimented. For example, the use of explosive, the use of caterpillars, and probably in that experiment there was a lot of use of explosive that probably now is not so important, because the use of explosive is very expensive. But probably the use of caterpillar is effective in the same so it's more cheap, and also can be effective. So there are many things that were explored that were costly, of course, but gave us a lot of information. Probably in the future, a diversion could cost less than in the past.
May I just add something? Well, I completely agree with what my colleague said just a few minutes ago, and with the last speech of Giovanni. And first of all, in case it should happen again, we must consider that, first of all, it is a political decision, rather whether to save an infrastructure like Effusive Sapienza or not. While in case of the treatment of a village, it is different, of course. And it is really true what Giovanni said about the advantage to divert the lava flow close to the vent rather than on the front. At the same time, we also have to consider the logistic aspect. because sometimes reaching the highest level, the highest elevation is not so easy. To reach there with the machines and all the means that are necessary. But it's always a matter of finding good balances between the best position and the logistic, you know. And anyway, what I agree also with that probably nowadays we wouldn't use no more explosive. Also because in the last decades we gained an experience, and what we saw is that what worked better are earth barrier, earth dam, and moreover, what worked better is not the earth dam built in perpendicular and with respect of the direction of the lava flows, but something that can let's say divert, let's say accompany in brackets the lava flow in a different position, because the perpendicular barrier had the effect to slow down the flows to allow more time to do other things. But if the flow continues, it will be the dam will be overcome first or later. And while another big problem is that if we have, as Domenico said, the opening of a fracture at a lower elevation. But in that case, we hope that we will have some precursors well before, but in advance. Let's hope. So we could prepare a plan or evacuate people even before the event opened. Obviously, nothing is for sure, but this is what we are confident.
If I can add just one.
Just a short answer, please, Sonia, because we have two other questions waiting.
Just to point out that what was really underestimated at that time during the 91 to 93 eruption was also the growth of lava tubes. There were a number of flows covering the earth dam because there was a lava tube inside that was not detected at the time of the eruption, and this caused a major problem. Okay, I finished.
Okay, thank you. Stefano and then Benjamin. Stefano, you have a question, I understand.
Yeah, but Lucia almost stole me the question. I want to ask to Sonia about exactly the applicability of this method used in 2002 in the south flank. Why, for example, didn't use in the north flank during this eruption? For the Piano Provenzana, I'm thinking. Okay, for sure.
No, we did. During the, actually, in the north flank, during the 2001 eruption, 2002 eruption, there was an earth dam built up by the civil protection, but it was a sort of favor given to the population. The population were fearing for the lava flow approaching the village, and we said it won't arrive to Lingua Glossa. But the population was scared anyway, and the civil protection decided to build this small earth dam that was removed after the end of the eruption because eventually this earth dam could collect water and cause floods instead.
Yeah.
So it was just built up in a short time for the population and removed after the eruption because it was useless. The lava flow was going in a different direction.
Yeah. Okay. Well, the other part is already replied by you and Domenico. Thanks.
Yes, thank you. Benjamin, you have also a question.
Hi, thank you very much for both your presentation. It was very clear and very interesting. I have two short questions for Domenico. First one would be, does the scientists from the high-risk committee participate in the monitoring? And the second one is, it seems that the alert system is including all monitoring parameters, but I was wondering how they are automatically integrated what is the weight, for example, of seismicity compared to SO2, compared to tilt or to thermal? Thanks.
Thank you, Benjamin, for the questions. Okay, for the first one, so if the Commissione Grandi Rischi is inside the monitoring, the answer is no. They do not do the monitoring. They are just called, they are on demand. Okay, so if there is a situation, in which the head of the department is needing an expert, needs an expert evaluation, then they call the Commissione Grandi Rischi, obviously. Then we will have this big meeting in which Commissione Grandi Rischi interacts with the monitoring institutes. So basically INGV and University of Firenze. So they will present the situation and then they will do their own evaluation, okay? Sorry? Okay. So this, I think, I don't know if I answered your first question. The second question about the alert levels. In the alert levels, it's not written which parameters interacts with what. Okay, in the alert levels, there is nothing automatic. It's always on a decision, on a collegial decision of who participates to the call conference. Okay, and it is based basically on the observed phenomena, and it's based on the recorded monitoring data for a certain period, and it's based on the past experience of those parameters, what they have done. Okay, it's just on it's based on the scientist experience.
Okay, thanks very much.
Thank you. There was another question from Oriel, I think. Oriel?
Yes, thank you very much. I had a question about the lava flow modeling, of course, but also about the communication to the population. So first question, each time there is lava flow going on, Sonia, you run a modeling and you have an estimation of where the flow will go. This map is communicated directly to civil protection and to the public, or does it stay first in between you to see which area could be impacted? For now, if it stays far from habitation, I think it's not a problem, but if habitation will be a threat, and what will be the communication?
No, obviously we give the information to the civil protection. It's the civil protection that decides how to transfer this information to the population. This is very clear and very strict. There is no direct contact between the scientist side and the population. And it's good that it's in this way, let's say, because it's a clear responsibility in this way. So we use the lava flow simulation in two different ways. Probably I didn't manage to explain well. As soon as we have one vent and the effusion rate, we run the simulation of the lava flow to see where it goes. But we have also already stored 30,000 simulation of lava flows all around the volcano in order to build up immediately a hazard map as soon as we have the position of the vent and the spreading of the lava. I don't know if Domenico wants to add something.
No, Sonia, I think you have clearly highlighted what's the procedure. And as Sonia said, this is in the procedure box I show on the presentation. It's within the agreement that we have with INGV and the other research institutes. So this kind of information is usually delivered in the special advices or the which are sent only during a crisis situation. And this kind of product is not published on the internet, for example, like or the social networks. Instead, like, for example, the normal weekly monitoring bulletins that are they are normally published after they have been sent to us. So for this type of products, there's a strict procedure.
Thank you. There is a last question on the chat, and that will be the last before going in Iceland. A question from Anna Dietrich. Are there legal implications for diversion in Italy for where the lava ends up going? It's about the legal implications. Who want to answer?
Obviously, yes, because you cannot, the first diversion was attempted on Etna in 1669 because the inhabitants of Paternò was trying to divert the lava, breaching with a pole the levees, making it go in a different direction. And there was a riot because of this, obviously, because you cannot stop the lava for going into your home and then letting the lava go in another house. Obviously, so now this is it's a rule. That's why Domenico said it's a political decision. Is the government that decides who to protect and why, and if it's really worth the expense. So now it's impossible to divert the lava towards another village. So that's why it's probably unique, the attempt that has been done in 91 to 93.
We had just,
okay, thank you. Yeah, very shortly, please.
Even in 2002, when the lava flow was at a very high level, menacing only the Rifiuto Sapienza, we had a lot of problems with the Parco dell'Etna, because there is a regulation in the park area. You cannot move anything. So before letting us doing this dam, it was a very long negotiation to do everything within the existing road, And in some occasion, even the ordinance for the law for civil protection cannot overcome ordinary law, such as for environment protection, like this. So it's really a mess.
Okay, yeah. Olivier, you want to have a comment about that? Olivier is a lawyer.
Yes, thank you, Patrick. Although in France a lava flow diversion was never attempted, it would certainly the regime of strict liability of the project owner would be certainly applicable. The strict liability, that is to say, there is no need to prove any fault of the project owner, and the project owner in this case would be the French state for this. Yes, if you want, I can put the case law on the discussion.
Okay. Thank you, Olivier. I propose to stop here. We will take 5 minutes to see with our Icelandic colleagues if every well is working. You have time to take a coffee, for example, and we will start again at 11 French time. So just 5 minutes. Yes, Oriel, I leave you the floor if you want to say something.
Okay, yeah, no, just 5 minutes. You can all have your coffee. And Armand, please, we just check everything is working with your sharing screen?
With pleasure.
Yes. Will you give the presentation, or you will share with other people? Oh, Thor is here.
Yeah. I see that Armand, Thor, and Palais at least are online.
Okay.
I don't see Olaf, but.
Yes, great. So you will all share your screen, or just one? It's just to know.
Hi, Palais.
Nice to see you. To begin with, it will just be my screen. So.
Okay, perfect.
Yeah.
Okay. Thor and Pele, your microphone are okay?
I will take a coffee.
Well,
yes.
I think my microphone is okay. I'm good. Yep.
Okay, cool. Pele, can we just make a sound test?
Hi. Do you hear me?
Yeah, very little. It's very low level.
Okay.
we hear you, but it's very low. So
I'm not the main speaker, so it's
okay, but that's fine. We can still hear you.
Yeah.
Thank you. Okay. So I will also get my coffee. 2 minutes, Arman, if you want to start sharing your screen.
Yeah, how do I do that?
How do you do that?
Yes.
You'll be able to do it now. Sorry, I let you. So you can have this little share screen to the bottom. Can you see it?
Yeah.
Share screen.
Okay. So no problem. No problem.
Perfecto.
No, it's this one here. So you should be seeing my screen, isn't it?
Yes, we see it. Perfect. We see the PowerPoint.
Yeah.
If you
So
click
if I
here, I
put
think it's gonna be fine.
Yes. Okay, so
Yes,
everything
that's
okay.
fine.
Yeah.
Yeah, everything is okay.
Yes.
Perfect.
Then I'm just ready when everyone has had their coffee.
Yes, give us 3 minutes. We grab a coffee and be back.
Perfect. No problem. Then I can get a coffee also.
Okay, on attend. Let's wait for Arman to be back with his coffee as well.
Are we ready?
Yes.
Are we ready to go?
Yes. We are just in time. We can start if you want. We have about 1 hour and a little bit more, if necessary, to this presentation and the question. So we have time.
Okay.
Arman, the floor is to you.
Thank you, Patrick. So what we are going to present here is a little bit result of this project, vTools and Eve, and as well Eurovolc and FutureVolc and all that, and what we've been doing in trying to assess volcanic hazard in Iceland, which has not been done in, so to speak, in a systematic way. In these projects, we decided to take the Reykjanes Peninsula for an example in using the methodology that we are trying to develop within vTools and Eve. If you look a little bit, for those of you, of course, many of you have heard this before, but some of you are new. So Iceland is a little bit special place in the world, like, well, every place is. It's an island in the middle of the Atlantic. And when we look at this map here, we realize that Iceland is something not really what we would expect from the point of view of plate tectonics and all the big theories. We have the division of the North Atlantic, which comes here from the Charlie Gibbs and up to Iceland. And then we have a division of the Northern Atlantic in the north of Iceland. But Iceland itself is this huge blob in the middle of the Atlantic, which explains in a way why we have so many volcanoes in Iceland. It's a big island. It's 110,000 square kilometers approx. So it's not when we talk about island, it is not a very small thing, Iceland. Yeah. Now, the Reykjanes Ridge, we are going to focus on that. The Reykjanes Ridge is out here. And it is, of course, a combination of complex tectonic processes and volcanic activity. This here is the Reykjanes Ridge, the submarine part of the Reykjanes Ridge, as it is getting shallower and shallower and coming up to Iceland. And the volcanism on the Reykjanes Ridge is a very typical basaltic volcanism. It's not very frequent. It gets less and less frequent the further south we go. We see more and more of volcanics as we come closer to Iceland, and the ridge comes closer to the surface. We are going to focus a little bit, start by focusing on this area here as the ridge hits the Icelandic shelf. And as soon as we come to the Icelandic shelf, we start to see the first major volcanoes. Here we have a volcano called Njörður, which is just at the shelf edge. And we see here a huge caldera in the structure. We have, of course, the dividing part of the plates, about 10 kilometers across. And we see all these little mountains here and craters, which are, of course, representing the volcanic activity at the plate boundary. But having a caldera means that we have a kind of a magma chamber closer to the surface than we would expect. When we come to Iceland itself, the Reykjanes Ridge comes in here. This is the Reykjanes Peninsula, which we are going to talk about. And as we look at Iceland as a whole, we see that these bluish parts here are the oldest parts of Iceland, dating out here in the west to 18 million years old, and to about 16 to 17 million years out here in the east. But the volcanic activity of Iceland is focused on small areas within Iceland itself. You see the Reykjanes Ridge and extending here to the north. Then it crosses the center of Iceland, and we have a much more active part here in the east of Iceland. Now in Iceland, due to the complications and due to the number of volcanoes, we have the decision was quickly made to divide Iceland, the volcanic part of Iceland, into swarms of fissures and faults and craters and central volcanoes. And that is what is represented here, these brownish belts. These are all separated system of faults and fissures and volcanoes. Coming to the Reykjanes itself, here we see steam coming from the drill holes on the western extremity of Reykjanes, which we are, of course, harnessing for geothermal power, both for electricity and for hot water. Now, the Reykjanes itself is in a way very special compared to the rest of Iceland, because we don't really have any major volcano, central volcano, like I showed you earlier in the sea. The first major volcano is located out here in the east, but on the peninsula itself, it is mostly characterized by fissure and faults and a row of craters and lava flows, etc. And we can easily distinguish the different, that is by the density of the faults and fissures, we can easily define basically three main splitting areas of the peninsula. Now, looking at the geology of the peninsula, we see, which is here, this is the Reykjanes Peninsula, and we see that basically the peninsula is 100% volcanic, so it's only made up of volcanoes. We know that we know of one historic volcanic period on the peninsula. It started around 900 AD and started in the east of the peninsula, and then gradually moved to the west. So the first one was is the fissure swarm that is out here. That is we call Bláfjöll Brennisteinsfjöll. The second one is here within the Krýsuvík system. That is a system of faults and fissures and volcanoes running up here. And this system actually started to show activity in 1999. When in this is a solfatara field within the system, and we had some geothermal explosions in this area. Now, the last one in the historic part is active out here in the west, within the Reykjanes fissure and fault and crater system. And there are several eruptions that take place out here during this period. And after this, the peninsula is more or less quiet until the early months of 2020. So this is the extreme, this is this extreme of the peninsula out here, where we see here the geothermal activity, we see the graben, here the ridge is coming on land, the Reykjanes Ridge, the Mid-Atlantic Ridge, comes in here and splits it up in two. So Reykjanes Peninsula, why would that be important? This is the most densely populated area in Iceland. We have, in this area, we have the capital region, and then we have several other important towns around it. And total population here is close to 200,000 people. Compared to that in Iceland, we have only 340,000 people living. So this is, although it's a big island, there are not so many people living there. And most of it is in the mountain, and people don't live in the mountain, they live along the coast in Iceland. So it is, of course, important to understand the volcanic activity of this peninsula, since we are very close to the densest population. And of course, that means also that very important infrastructures are located on the peninsula, which help us living in Iceland. Both the groundwater that we are using as tap water, all the hot water that we are pumping out of the earth to heat up the houses in the peninsula, which of course is very important for Iceland, because we don't have to buy oil or coal to heat up our houses, we just pump it out of the ground. So that is the decision to go into this peninsula and try to apply this methodology to define the volcanic hazard on the peninsula. And we use the setup that was made in V-Tools and Eve, and basically gives us where we are today. Basically, we are here we've done the long term for the whole area, and that, of course, allows us to go into short term as soon as something starts to happen, which we did, of course, following the unrest that started. So basically, this methodology allows us to define the hazard and the susceptibility of, for example, vent opening, etc. And we can start to run some simulation models to see what is at stake in the area compared to our geological compared to how we have analyzed the geological data. We have not reached the end of this, which is the vulnerability analysis and the decision model, that is cost-benefit analysis. So we are with the Reykjanes Peninsula, we are here we come into the hazard area. So still a lot of things to do, but still it was good that we had at least finished the long-term analysis, so we could go into the shores. So another simplified image to show what we have done so far. We've taken all the geological data and put that into a context. We've done the volcanic susceptibility analysis, and now what we are able to do, of course, is to apply eruption scenarios or simulations to calculate the probability of something happening as soon as the peninsula comes to an unrest. So if we look a little bit here, we look at the western part of the peninsula, where close to the area where our actual eruption is. Then we see here, we are looking at the susceptibility based on craters and crater fissures, and we give them both 50-50, the wavelength of 3 kilometers. That shows us that this part of the peninsula is very vulnerable, because what we are doing here is to see what our data can do. So here we have the wavelength of 500 meters, and we start to narrow down the most likely areas. Here we go down to 250 meters, and then we start to really see where we have the most vulnerable areas or hazardous areas on the peninsula. Now here we have taken we still have the 250 meter wavelength, but here we have divided the craters and crater rows into 3 categories. That is very old, around 2000 to 2,400 years old, and then the last historic. So the historic have 70% value in this calculation, the next has 20, and the oldest one has 10. And so that still helps us to narrow what we are seeking, that is, where are the most vulnerable areas or susceptible areas to have an open vent, and from that we can start to do the simulation to look at what is at stake around it. So let's go a little bit here, Doug. So when we are looking at the whole of the peninsula, which we have also done, then we take, of course, all the geological and geophysical data that are available for this kind of an analysis, this probability analyzed with a probability density function. Here we see we have these are volcanic vents or craters and crater rows divided according to their age. So the historic ones are red, then from 1900 to 2400 BP, they are green, 700 to 900 AD, they are yellow here, and older than 2400 are these in the pink. So we have to gather all this data into the into a geo-information system, GIS, to be able to start the calculation with these. Same is done with the fissures. These are all fissures on the peninsula, and we start to see, of course, that there are denser areas and less dense areas. And if we look at only the youngest fissures, we see them that they are, of course, the youngest fissures. Now we are just looking at the fissures that we can identify in the youngest lavas on the peninsula. And that still gives us, of course, an indication where the youngest movement of the crust, upper crust, can be identified, because if we take the whole, the bulk of the fissures, like here on the Western Peninsula, we see there's quite a dense fissure swarm here. And basically that is because it has never been covered with new lava. So these are fissures that we know that oldest fissures of these, they are more than 14,000 years old and have been moving more or less ever since. Geothermal areas we put in as well, and here it is, of course, the high geothermal areas that are of importance. They are less important, these areas that we have here in the north. They are all in the old crust. This is low temperature areas, while here on the peninsula itself, we have high temperature areas. And here we look a little bit on the western part of the peninsula, and we are looking at the craters and age of the craters. and what bandwidth we can use to analyze the data. So it is different data basically because we have less events in our analysis. Older craters tend to be covered by younger lava flows, etc. Same with the geothermal part and with the faults and fissures. There we can get the densest or smallest bandwidth because we have so much data on the faults and fissures. And if you take just the youngest fissures that we see, the bandwidth gets a little bit larger because we have fewer data, of course. So the susceptibility analysis from this, we have here three results for the Western Peninsula, and they are of course based on different ages of the crater groups. So if we look only at the historic part, our susceptibility map will look like this. If we look at the craters that were formed 2,400 years ago, we see there is a slight change. We have there is a movement here. This is an area called Sundanúkar, but still we have the activity here in the extremity of the peninsula. And if we go to everything older, of course our data are going to be expressed a little bit different because these there are less of these craters are preserved. And similar is with the fissure and faults older than 2000 or younger than 2400, and same with the geothermal areas. So if we mix all this together to get our susceptibility, we divide the eruptions basically in three categories. The youngest one having highest value of 30%, the middle is 16, and the oldest are 13. With the fissure and faults, they are also divided into the densest and youngest, and there the densest part gets almost 10% value in our total calculation. The youngest have 14% value, and of course they are more important because we can define the movement of them by the age of the lava flows that they are breaking through. And then geothermal is given 16%. So this is the result of 12 scientists that were giving basically these 6 different information and asked to evaluate what is their value if we were thinking about the probability or the possibility of eruption in the future. So if we look at this, this is basically the result map, that is the susceptibility map of the western part of the Reykjanes Peninsula. So the red zones are telling us that these are the areas which are most likely to host a new vent in the future. And of course, the colder, the less likely. And we see, for example, in this area, there is practically no possibility that we will have an eruption up here. And that is very nice because that's where the international airport is. But note also this area here that shows up here, because this is actually the area where the vents opened up a few days ago or weeks ago. But still, we are getting a signal from this analysis that this is an area where we might expect an eruption in the future. Looking a little bit at the people, where is the people compared to where we are expecting the eruptions? Here in Grindavík, there are about 3,200 people living. Here in Reykjanes, 16,000 people. And here in Vogar, 1,100 people. And Hafnir, 112. So basically, there are 2 towns here that are close to the vulnerability areas or to the susceptibility areas. That is the town of Grindavík and the town of Vogar. Practically all the other towns here, they are way out of the susceptibility analysis zone. Here we are looking at the tourists, basically. We have lots of tourists in Iceland when there's not COVID, and these are the most frequently visited sites in this area by the tourists. This is a bridge between continents, sitting, of course, here in a high susceptibility area. There is this Gunnukver and Brimketill out here, and then Básendi and Garðskagi. So these are the most popular visiting sites at present. Now, of course, this area here where we have the eruption is going to go up by tourist visiting once the COVID is over. Looking at the infrastructure, of course, there's quite a lot of roads. We have power plants out here, we have power plants out here, and we have the Blue Lagoon and all that. So basically, important infrastructure is close to these high susceptibility areas. These are the two power plants, and these are the power lines, which are of course crossing this area, making the power lines vulnerable in a future eruption. So the total of the Reykjanes, susceptibility analysis of Reykjanes looks like this. Here we have Reykjavík. So we have possibilities, of course, of opening vents close to the greater Reykjavík area here. And of course, an analysis that has not been finished yet is to look at where lava flows could actually go, but we have started that, and we know that in this area here, the highest vulnerability is here, this part of the greater Reykjavík area. But there are other things that we have to worry about, etc. But so here we are. When everything started, it began in January 2020, when we were actually on our meeting with Eurovolc in Catania. We started to see marks of magma accumulating, basically in the area out here, close to Grindavík, and lots of seismic activity was taking place. This continued then erratically throughout the year 2020, but not with any really drastic thing until 2040 this year. Then basically everything went havoc on the peninsula. We started big earthquakes, and they were tens of large earthquakes every day after 24th, and basically everything was shaking. When you were walking, it was like you were either on a boat in a very bad weather or completely drunk. So we had very high intense activity from the 24th of February. We saw the first tremor on the 3rd of March, in this indicating that magma was getting close to the surface. And this is basically a lava flow probabilistic map that was generated after the tremor of 3rd of March. So it is in this area, and basically what we did was issuing these lava probability maps based on the eruption susceptibility, which was calculated from the long term with addition of the location of earthquakes that were taking place. And of course, the eruption started late evening on the 19th of March. So we had several weeks of earthquakes, strong earthquakes prior to that. And the eruption started basically here in this point. So February 26th, when we start the calculations, we have, of course, the long-term analysis, and the most intense earthquake activity is in this area. So the recalculation of the long-term susceptibility gives us this short-term. So still we have very high areas that are, or large areas that are prone to erupt. And we run immediately the calculation, expecting a lava flow. We run a calculation of the lava flows with a 500-meter grid within the red zones here. And that gives us that the lavas can possibly, where they can possibly go. And here, of course, the color, that is the grayish color, is less important than the reddish color that we are seeing here. And we do this every day, actually 2 times a day. It was done in the morning and in the evening, but we only publish the morning forecast because, people have to be able to go to sleep, etc. And here is the February 28th forecast. We have basically the susceptibility is starting to focus in this area here, but still we have quite a large area. and we do it always the same. There's a 500-meter grid within this area where we start the eruptions, and the result of that calculation gives us this probability map for where lava can go. And in this case, we see that it's heading towards the north. We have power lines and we have important roads in the north that can be damaged. And of course, we have some infrastructure as well, like in Vågar. So doing this every day, here is from the 9th of March. And we have these two spots here. We let erupt in them, and this is the result that we get. Still, something can be going to the north, but now most of the lava, if they erupt within this area here, are going to go to the south. The good thing of this, doing this, was it really woke up people very long beforehand, and realizing that what could possibly happen, because this is forecast and we are just pointing out that this is something that might happen. And of course, the governmental institutions started to react, seeing that actually we have a possibility of something hitting something that is important. It's not going to be just in the mountains. And so it started really a project which start to look into if we can protect the infrastructure that that is threatened by the eruptions, or if we, how fast do we have to evacuate areas, and how do we really have to react in all this. The final calculation was done in the evening of 19th of March, and around between 8 and 9 o'clock in the evening, we got the eruption, and we see this is the result of the final calculations. We have the largest area here within where everything started on the 19th of March, and we have smaller spots here in the north and in the southwest of it. So this basically worked quite well, I must say, and it was in a way a luck that we had already made the long-term forecast. This is the first probability map that we issued then once the eruption is clear. We know that where the eruption is, we don't know how much magma is coming out, and we don't know the length of the fissure, but still we can run this, basically we run cool lava with FlowGo, which basically gives us where are the most likely areas for the lava to inundate. And we, of course, get this Valley Geldingadalir here, and this is the Valley Meradalir. This one is filling up, and it's starting to overflow into this valley here. So, worked quite nice and successful story. Here is the video that we took during the night. The eruption started in the evening, and of course, like always, we are not completely ready. We have to react. And it took us quite a while to gather together, and the weather was horrible. It was impossible to get on land close to the vents, so we had to send up a drone that could fly almost 4 kilometers away from us, and these are the drone images taken during that night. So we are basically, we are 2.5 kilometers away, and only watching this basically from the drone video. But this is good. We see immediately that this is not a very intense eruption. We see it's calm eruption. The fissure is divided already from the first minutes of the eruption. The fissure is divided into several craters. Normally, a fissure eruption in Iceland starts by a curtain of fire along the whole of the fissure. That did not happen here. And so the first images and analysis that we are getting there in the middle of the night gives us a reason to be a little bit less stressed, because it's not a very powerful eruption, and it is not a typical Icelandic fissure eruption starting with curtain of fire. This is just a few hours after the eruption started, and we can see that we have several craters here which are all separated. meaning that they, in the shallowest part of the crust, they are not connected. They must be connected a little bit deeper down than that. Yeah, let's just finish watching this beautiful video. And we see, of course, lava is flowing away. There is no major explosivity. This is just the blubbing craters that are issuing basically lava up on the surface of the earth. It's almost finished. So fissure eruption or effusive eruption, calm effusive eruption in Iceland. Normally, if there is an eruption in Iceland, people flock into the area, and this was no exception. As soon as weather got better, people started to pour into the area, and we see here a lot of people. This first day of the second day, this is on Sunday, second day of the eruption, and then already there were only 2 craters active. That is the 2 main craters. Other craters are turned off. And we see here one of the cracks that is steaming, which followed this opening of the crust there. But again, a lot of people coming in. And usually in Iceland, what happens is that the police commissioner, the civil protection, and the search and rescue teams gather together to try to control. And you see the people out here. This is the search and rescue teams that are out with the people, trying to help them and advising not going too close, etc., to avoid any accidents. And this one here is taken 4 days ago. And we see, because this is a slow effusive eruption, access to it is very easy. And of course, people, when they're flocking in, they tend to go as close as they can. And it's very difficult in a way to stop that, because there, as of now, there are tens of thousands of people that have walked up there to have a view at the eruption. This is taken 2 days ago, when these are new craters. That is, as it is going, we are getting new craters within a length of around 800 to 900 meters. That is from the southernmost crater to the northernmost crater. And regularly we are getting new and new crater openings on this crack, which basically indicates that the first craters that opened up, they are not powerful enough to lower the pressure in the system itself. So the eruption is here, out here, basically in the best place ever possible. We are far from all of the infrastructure, Reykjavík being out here, airport being out here, Keflavík and Grindavík. Calm in the mountains, take you about 2.5 hours to walk from this area here into the area, and nothing is at stake at present except tourists visiting the area. That is how it looked like. This is 4 days ago. So these are the craters that opened first, the 2 over here. This is the northernmost crater that is issuing lava into this valley called Meradalir. This is Geldingadalir here, and the valley is slowly getting full. We started the openings that took place 2 days ago, occurred here in the slopes, and they are now issuing lava into this and here towards the east of it, which will eventually pass the path here and go into this valley as well. So good that we have finished the long term. It can help us to predict and analyze what is going on, and help us to be ready to build up, to be ready to react when we get the eruption close to the civilization, that is close to something important to the people that are populating Iceland. And I must say that so far, this is basically the first work of this kind that has been undertaken in Iceland. And hopefully we will be able to do more of this with the other volcanic areas to help us being ready and foresee a little bit the possibilities that are at hand once we get an eruption. Thank you. So I finished, Patrick.
Thank you, Arman. Put my video on.
We still have time, don't we?
Yeah, Thor, you have something to present now?
I was just to finish this off. Maybe is to show people a time lapse of the first days of the eruption.
Yeah, we can do that. We will have the question after all the presentation.
Yeah. No, it's just if let's hope I can do this. Let's see.
You should be able to share your screen now, so I just let you do it.
Yeah.
Then the bottom, Thor, green thing.
I know. I don't know why the video disappeared, but it did. Okay, here we go. So this is a timeline from the early days of the eruption.
So we don't see it. You need to click on screen sharing and then select the window with the video. Yes, perfect.
I know I always forget there's a two-step process in Zoom. But anyway, here it is. It's very short. But it's quite informative about how the lava is actually advancing, and there's a lot of really neat information in there about how the lava sort of grows. Something that we're looking very excited about in terms of analyzing. Happening very fast. How was it? Let's see. How do I stop sharing here? Here we go.
I did it for you.
Yeah, thank you.
So, any questions?
Thank you for this video, and thank you for the presentation, which show very concretely the contribution of the EVE project. Yeah, maybe we have time for a question now, and you can also ask a question about the eruption, of course, about what Arman has shown to us, and about the problem of civil security, because Pele is online, and she can also answer the question. There is some hands up. Auriel, Domenico, Benjamin, Lucia. We will start with Auriel.
Yes, thank you. Thank you very much for the presentation. I was wondering, as it's far from everywhere, and as you said, the tourists are the main concern. So what are the actions that the civil protection took, and you and communication, about how to deal with the tourists to avoid accidents?
Yeah, I think it was quite a surprise, although the peninsula, okay, we have finished this long-term analysis and all that, and we have been having these small intrusions that were showing up on interferometer analysis, that is the SAR analysis. In the beginning, everyone was more or less convinced that this was only a tectonic event. And then later on, we start to see the signal of the magma and all that. And we must say that, at least from my point of view, the reaction was a little bit chaotic. We are, of course, a small nation, And therefore, all our institutes are very small. And our Civil Protection Institute is very small, although it is divided into several. And they have been working very, very hard with this COVID-19 thing. And everyone getting really, really tired, been working for a year on that, etc. And then all of a sudden we get this in. And that was basically, because it's close to population, this is, last eruption was much, much bigger than this, but it was high in the mountains, so it was not threatening anything. Now we are in close to the population, clear that many people can go there. You cannot stop people from going. They can walk in from everywhere. And so the thing is that we started very intense, I would say, wasn't 2-3 weeks that were very intense, both with the health authority to issue out the gas things and then what are at stake when you go up there. Then working with a group on the infrastructure to try to identify what we can do and what we cannot do, etc. With the environmental agency, etc. So basically the first 2-3 weeks were very chaotic, while people were deciding what information we should send out and how should be warned, basically because everyone is going. You know, out there, sometimes if you look at some photos that you can see on the internet, there are thousands of people out there the same day. And it's beautiful, you know, it's calm and but there are several factors that are dangerous. The gases in good weather, they can accumulate. This is valley landscape, etc. So there, you know, everyone had to react so that we could be calm with people visiting the site. And that took almost 3 weeks. So now we are getting a little bit more calm, I would say. All the information have been issued. All the institutions of the state have a comment on that is regarding their responsibility on how people should behave due to the eruption, etc., etc.
I can maybe add a bit to that. The on-site people are, most people are behave responsibly. There are a few that don't. But the view that we have taken is that we give people advice, we inform them about the dangers, we tell them, you know, what they should, you know, avoid, and then it's more or less up to them to follow those things or decide what to do, how much risk they want to take in terms of getting close.
Oh, is that you who advise, or is that the civil protection? Who is advising and who is allowing or not to get close, or it's whatever?
No, it's always civil protection.
Okay.
The only thing we do as scientists and the as a group of scientists, we provide the civil protection and the authorities with information about what the potential hazards are and where the dangers are. And then it is, you know, the authorities who actually make the decisions. And some of them are not necessarily very clever because in the beginning, they decided to have people walk into the eruption site from far away. So they had to walk over lava flow fields, etc., 7 kilometers, which actually produced new hazards, injuries, and you know, breaking your leg as you're walking across a lava flow, and exhaustion with people just walking for that long. So it was 7 kilometers one way, and then back, and in cold weather and things like that. So they changed that, and they learned fairly quickly and changed it. So I think, like Arman is saying, I think we are getting better at this, but we still got a ways to go in terms of managing the crowd.
Thank you. There is a question from Benjamin. Benjamin always asks questions.
Yeah, I'm sorry about that, but I'm very interested in this topic, and thanks a lot for the presentation. The images are spectacular. I wanted to ask you, how did you update the susceptibility map during the unrest?
Come again?
How did you update the susceptibility map during the unrest to produce your
what we do
inundation map?
is, during the unrest, we have the long term, which is always in it. And after 3 calculations, that is, the long term has a value of 40%. And then the new events, which are the location of the earthquakes, have 60%. But since we are calculating 2 times a day, it means that long term is 40%. The newest earthquakes are 40%, and then the last calculation is 20%. So we are mixing, so there is a memory in the system, and that memory, well, we can never take out the memory of long term, which are the geological data that are in front of you, but the memory of new event is getting out slowly. It does not disappear completely immediately. We take it out slowly. And
you don't use ground deformation?
We didn't have access to those data. So, yeah.
Yeah, it would have been nice to include that as well.
We actually got one such an image from Czechoslovakia, because we couldn't get that from our colleagues that were working here. So we got one image from Czechoslovakia, and of course we got better resolution. That is we got narrower, the area that was prone for eruption got narrower. So it would have been good to run the INSAR results with it. Yeah.
Then we have question. I know that Lucia is waiting, and Julie as well, but we also have a lot of questions on the chat, and I want to ask this question before they are gone. I think that the first one was from Hannah Dietrich. If I'm right, yes. You have published hazard map publicly. Have you published hazard map publicly? How well have they been understood? What sort of information has accompanied them in the term of explanation? Who want to answer that?
Yes, I can answer that. We started immediately to publicly expose the maps, etc. And of course, when we started, we understood everything. So the first maps were more, in that way that you think that everyone understands everything as well as you. We got lots of questions. We always answered questions, and we used a Facebook page that is for the volcanology and natural hazard group in the university to do this. And so every time we published a map, someone had to sit in front of the computer for 3 hours to answer all the questions that came up. And so this was done categorically throughout the time. And little by little, we were getting suggestions from those that were reading how we should explain them better. So we added always more and more explanation according to the people that were reading our page. And in the end, I must say it took very well, because in the end, the people that were following the page were quicker in answering the questions than we were, because they understood everything. And if there came a new person in that didn't understand, they answered immediately. And then if somebody, like, these monsters on the internet started to attack a little bit, but they were completely taken down by the viewers of the page. So we didn't have to do anything there. The viewers of the page took them completely down. So it was a learning process for us and for the people that were following this.
Okay.
So in the end, we explained the methodology behind it and all that in a reasonably straightforward language, and what there was, what we were trying to do with these predictions. And as Arman says, it was a success because I think we had up to 60,000 hits on the page at some point. So people clearly following it and reading it, and also got very good reviews from the locals, like in town of Grindavik and all over. They were because no one was providing this information. No one was actually telling them what might happen and what, if an eruption took place, what is the possible flow of lava, etc. So they were actually quite grateful at the end for getting some information about what might happen if there was an eruption.
Okay. Another question on the chat from Jonas Biren. What would be your reaction, and that of the civil protection, of course, if the new lava eruption extend to the geothermal pipes?
Yes, we would surely start.
Watch the lava go over the geothermal pipes. There isn't much to do.
Yeah, I think. A question from Andrea Bevilacqua. How did you choose the weights assigned to the various components of the long-term vent opening map, susceptibility map? Was there an uncertainty range for them? It's a question for Arman, I think.
Yeah, that was done basically. There were 12 scientists. There were 8 from Iceland, and the rest was from Europe. That were given the different. I showed you the different information that we were basing it on, and they were just given a questionnaire what they would value that in comparison to each other. So a very typical, what's it called, expert evaluation was done. And that is the final result, that is the final value that we give for each part before we calculate the susceptibility map, is then based on this specialist evaluation. So we were, of course, happy with that, because after the evaluation by the scientists, we that were working on it were not necessarily, we did not necessarily concur with their opinion, but we did not interfere. So and I think it, at least what we've done so far is quite well, is working quite well. Of course, we can surely make things better in the future, etc. But it was nice as a pilot project, and getting the eruption in the end, that was very nice.
Okay, maybe Lucia, now you can ask your question.
Yes, thanks a lot about these talks, Arman and Tor. So a question. The first day we spoke about petrological monitoring. So my question is on that. How many times are you sampling the lava for systematic measurements, or if you do or not? And if you do systematically, how many times and in which way? Because we present a kind of protocol, and I would like to know in which way you approach this wide lava field.
Tor.
Yeah, can you, yeah, I'll try to answer it. You may have to repeat the latter part of the question. Now, the setup at the moment, as we have it, we have both experience and well-skilled people to actually sample active lavas. And we do that systematically, on average, every other day. But if there's some new breakouts and things like that, then we go in. We got a special kit that actually allows us to sample the active lava from a safe distance. So it has a long pole, and it works actually quite well. So, and people are wearing all the necessary protecting gear. And our sampling is primarily based targeting actually information about the properties of the lava. So crystallinity, vesicularity, things like that. We're less interested in the geochemical monitoring because there's another group that is sampling that, and they've been doing all the chemical analysis, and it looks like they are sampling at a similar frequency as we are.
And in terms of the location, because we said we try to samples at the front of the lava channel and close to the vent as much as possible. But also, when the conditions are ideal, we try to have a sampling along the flow to check for crystallinity, vesiculation variation. So because you focus on texture, are you able to do that?
Well, we can't, you know, in some instances, we've been able to actually sample along a lava channel. And it's quite useful, but a lot of times we just can't get to them.
I know.
But the other thing that we try to do is we document what we sample and what it represents in terms of the lava. For example, yes. if we're sampling active breakouts, whether they're on the side of the lava flow or whether they're at the active flow front, we document what that looks like. Is it toothpaste lava, highly viscous, or is it very fluid, pahoe, or etc. So that's all documented because obviously the more viscous the breakouts are, the more residence time they've had in the lava flow field. So you might then be sampling lava, which is actually, could be even a few days old. Even though it is actively breaking out at that point. Those are all kind of important things. So a detailed documentation of what you actually sample is important. And then also we have sampled tephra. There's a little bit of tephra produced by this eruption, including Pele's here, and we managed to get the good samples of that one of the days, and the wind was blowing in the right direction, and we could collect it from the slopes of the Buka.
No, great. We do like that. Thanks, Thor. Thanks a lot.
Thanks. Julie, you can ask your question.
Thank you. It's a question for Pele. I'm sorry if I mispronounce your name. I was wondering how you do use the susceptibility maps or any other type of info which is provided by the scientists to take concrete measures of civil protection, and how do you use these maps, these susceptibility maps, to communicate with the inhabitants in the areas which are the most exposed, like I think Arman did mention Vogar and Grindavik.
So, well, at the beginning, I want to say that this is not my area. I'm not working in this specific area in the Reykjanes. Now I'm in the northeast of Iceland. But as Arman told you, there was this seismicity nearly all year 2020. So people had been talking about it. The scientists had been provided some data like this maps you are referring to. So the difference now and often before was that the people was really prepared. They knew all about the seismicity. They knew really the hot spots where it was most likely to be eruption, and therefore they were calmer, I would say. People were not frightened, and they had this information just through. Some of it came just straight from the scientists, like Arman was telling you about, the Facebook site from the university. And so this information, they were really easy to get information about the status. So I think people in this area who live there were really watching it, and you know, it was always in the news, the seismicity, and people were really anxious when it was the biggest earthquakes there. So it was really, you know, it had a big place in the media here, all the seismicity that was in the Reykjanes last year. And so when at the end, the eruption began, people were quite, you know, they knew what was happening. They had been having this information. So it was no crisis with them. That they had been told by the civil protection that there are 2 ways to go from the town Grindavik, which is the nearest to the volcano area. So people were not afraid, as we found that at the beginning of the year 2020, when the seismicity started for real, people were really frightened at first. Then they started to hold meetings with them, civil protection and the scientists, and starting, you know, talking about what was happening and why it was, and all the things that you all know about the area and the ridge that comes up to Iceland, that through the peninsula and everything. So people start, you know, get more information, get some education about it. Where do I live? Why is this seismicity so strong here, and everything about that? So I think that all this information, and a lot of it which was came from this our project Eve, it was great to see when they launched the map from the, you know, probability plan from the about where the lava would flow. That was really, people really could, you know, be on ease with that, because it was not going into town directly. And yeah, in the long term, maybe the roads, but so people could, you know, sleep easy in their houses. I think that was the really important thing. And I don't know if Ármann and Thor agrees with me, but I think that all this information just changed the way people were, you know, feeling this and staying living in middle of it. So I think all this information we are giving them, and the scientists and the civil protection team and everybody together, it's vital for the people.
Okay, thank you, Pale. And
100%.
Yeah, we have time maybe for 1 or 2 questions more. Stefano Manini, you want to ask a question?
Yeah, thank you, Tore. Thank you, Ármann. I have a question about the airspace, because I was there during the first week on the eruption. And I remember several helicopters and the drone, and for sure are just not for research, are not also tourists. So I'm just wondering if the civil protection now introduce a few restrictions about the airspace over the site.
The short answer to that is no, but they do have rules and regulations. So both the helicopters and the planes are not supposed to fly lower than 150 meters.
Okay.
And drones are not supposed to go above 120 meters. Of course, depending on who, but quite a number of people, especially helicopter pilots, are breaking that, and they're also landing at the site.
Yeah,
I have not seen any official sort of a response or reaction to that from the authorities. And whether that should be done or not, that's also a matter of debate. I mean, how much do you want to allow them? And but there's been some close calls with helicopters and drones, and clearly the helicopter pilots don't like the drones. I think that is clear from how they act around the area.
Yeah. Okay.
I can add to this that the main rules about the drones is that you're not supposed to fly them over a crowd of people, but it doesn't say anything about volcanoes. So I think it's no rules about that specifically. But regarding air traffic, it's you know where the international airport is in Reykjanes, really nearby the volcano. So, and because of all the information we got and all the we could prepare ourselves because it's been taking so long. And when the scientists start talking about, like Ármann and Thor was in the media saying it will erupt, we just don't know when. So then people start really making plans, and one of the plan was, what if we can't use international airport, our international airport? Then our airport here in Akureyri, in the northeast of Iceland, we are an emergency airport for Keflavík. So we already had been held meetings because we have now so complicated system because of the coronavirus on our airport. So we have had already prepared ourselves to take some traffic and also to take some private air traffic to Egilsstaðir in the east. So it all comes to the same matter, that if we have enough information, and the more information the better for everybody, then we can prepare ourselves. And that's what's so great about this project, if you're working at. It's really, it shows in this volcano and the eruption in Reykjanes how it can be used. And now I will demand from Ármann and Thor to have such work done for my area. And everybody wants to have it, you know. So it's really exciting that we could see it getting used by this scenery.
Thank you.
Okay, there is a last question on the chat from Hannah. In eruption response in Iceland, how does the university interact with the Met Office for official warnings or official things? It's about the interaction between the Met Office and the university. Who can give an answer?
That's a very good question.
I know that.
Not necessarily easy to answer. How do we put this so we tell the truth, but not too harshly? There is a reasonably good communication between Met Office and the university, but the university does not really have any role in monitoring hazards in Iceland, volcanic hazards or any other hazard. So and what we do is always done under the banner of academic freedom. We do also pitch in and help the Met Office with the monitoring and especially when a crisis is on, then we often come in and pitch in. Now, so that it's a reasonably good interaction there. Of course, institutional politics also come into play, and it has to be said in all honesty, they have actually in a number of instances caused some problems and caused friction between people. So that and that's unfortunate, because the intent here is not to advance one's own agenda, but actually do the people's agenda, and that seems to be forgotten a number of times, and that actually includes individuals on both sides, both at the university as well as at the Met Office.
I see that.
Did that answer your question, Dimitri?
Stefano surely had a question. And are you in the scientific advisory committee?
Well, so one of the reasons I asked this is because I'm currently on the scientific advisory committee for Kilauea, the current Kilauea eruption. and something we're trying to do in the United States is because all responsibility for eruption, both monitoring and response, is from the U.S. Geological Survey, volcano observatories. But of course, the academic community can bring a huge amount of expertise and equipment and personnel into a response, but there is no formal way. The legality of, someone publishing a hazard map from a university, all of that would be very complicated. And so we're sort of building a structure right now in the United States between the academic community and the volcano observatories to be able to better do things in a response and especially plan in advance. So all of those topics are greatly being discussed right now.
Yeah, no, absolutely. And the scientific advisory board is a good way to do this, but I'm not sure we are doing it right though, because there are too many people in there, in my opinion, as it is stand now. I think every meeting has about 50 people. And, from all different institutions, and this is all coordinated by civil defense. It's not the Met Office. Met Office just participates in this as the representative for the monitoring side of things. And now it's used as a chat room about events. And I don't know whether that is the right way to go in terms of acting as an advisory board in how you're going to deal with the crisis. I think a better selected advisory board probably would serve the civil defense better, because they are the authority really, who and also the local sheriffs. Those are the people that make the decisions. I don't know, that's just my view of it. But it is an interesting experiment, and we'll see what people think of it at the end of it.
If I might add in, I think that scientists do not always agree, like you probably know. So I think it's better to we who have the responsibility to take decisions in these matters, that we can look at different opinions from scientists based on different maybe their education or some experience they have, or whatever they have the data, and they have lots of things to build the work on. So I think it would not be a good way if the one state scientist was to say that this will go, this volcano will erupt, it will go like this. And to listen to just one, I wouldn't feel comfortable maybe by that. So it's good that all the scientists really come together and with their data and their information for us who have to then make the decisions. Do you know what I'm saying? Yeah.
No, if I may add a little bit to it, Paula, that's a very good point. So, I think there is a really important to have a diverse views represented on the panel, and so it shouldn't be, even though I think it might, good to have fewer people. I think we have too many people in there, but we need to, all the different views in there. We need to make sure that that is covered, absolutely. And also, I don't think the advisory panel meetings are the right place to actually be discussing among scientists, different possible interpretations or views on the. But I think we need to have that as a separate thing, like a discussion panel where scientists hash out not necessarily the differences, but also just the different way of looking at the same data and analyzing it. So I think that's actually also very, very important. And that is not possible in the advisory panel meeting, because usually they are taken up by just people presenting their observations, not necessarily with much interpretation or actually in-depth analysis. They just say, this is what we measured so far. And that sort of doesn't come out as a good, necessarily as a useful advice.
Thank you, Tor. It's an interesting discussion. I maybe have a last question, if you want, before going to lunch. For us, not for Anna. For Anna, it's going to bed, I think. Arman, you said that the tremor start on the 3rd of March, if I remember well, and the eruption started 16 days later. And it's why such a long time between the beginning of the tremor and the beginning of the eruption?
Why such a long time? I think the Reykjanes Peninsula is not a normal divergent plate boundary. It's trapped between the Reykjanes Ridge and the main Iceland. And so before the magma could come to the surface, we had to release all the tension on the peninsula that was blocking the magma below. And little by little, we are releasing this tension. And on the 3rd, we get magma that is probably getting up to a depth of 400 to 500 meters to the surface. Because the deformation people had located the dike at the roof of the dike at about 1 kilometer. And so the magma is trying to get out to the surface. But the tension because we have this very strange transform divergent tension on the Reykjanes, the uppermost part of the crust was not ready to let it go. We had to finish the stress resolution or release the stress on the peninsula before we got the magma up. And we also see that the eruption is located outside the main fault and fissure zones, where we have the densest fault and fissures. So it's located at the edge. And we see that the holes that the magma is coming up, because as I mentioned, there was no curtain of fire in the beginning, which is typical for Icelandic fissure eruptions. It was not. From the very beginning, we had small vents that are oozing out magma. And we even see that these two vents that are situated in Geldingadalir, there is 60 meters between them. But still, the southernmost vent has a lava lake level that is, Tor, you correct me if I'm wrong, about 20 meters higher than in the northern vent, which tells us that they are not erupting on the same fissure. They cannot be. They must be fed by different tubes, although there's only 60 meters between them. So it is very special, Tor.
Yeah, they're two. Yeah, absolutely. They're two separate conduits.
Yeah.
Okay.
So the magma tried to get up on the 3rd, but didn't make it because we had to release more tension in the crust before the magma could really come up. Because this is heavy magma. This is olivine toluene, so the typical morb, very low in water, lots of olivine, etc. So the density is somewhere between 2.7, 2.8. So it's not a magma that you can easily drive up to the surface by the density changes when you start to release the gases. So this magma is releasing its gases just at the very last 100 meters. You know, it has started to release a little bit of CO2, but the water is not going out until it has, what, about 100 to 150 meters left to the surface. So.
Okay. I think there is no more questions there. I think we can close here this morning. I want to thank all of you for the very good presentation we had this morning and the discussion we have. And I leave the floor to Auriel for the last word and the afternoon, maybe. Auriel, you can finish.
Yeah, just thank you all for this morning. Just some announcement for this afternoon. We start again at 2 European time. We will start with a presentation of the result of the exercise. But even if you didn't do the exercise, you can connect. I think it will be very interesting for you to hear the results. And at 3, we will try to do a picture, a Zoom group picture, as we always do in workshops. So we will try to do it here. So put your best outfit and put your camera on at 3 so we can try this picture. And this will be followed by a conclusion by Joanne, Marty, and and Andy or others before to close this workshop. That's it. See you at 2 then.
Thank you, Auriel. See you.
See you.